Sharing my screen. Beautiful. All right. Can you see my screen?
There can.
Awesome. All right. Well, hi, I am Daniel, and we'll be kicking off with an introduction to Chapel. So when asked to make an introduction to Chapel, the first thing I did was go to the website and pull the tagline from the programming language into the slide, which is productive parallel computing at every scale. And today in this presentation, I'll be covering two things about this tagline, the why and the how. So why do you care about parallel computing, and how does Chapel help you achieve this? And how do you use Chapel to productively parallel, to program in parallel productively? So here's the outline of the presentation, which matches these two questions pretty well. The first half is, why is parallelism important? And the gist is, it can make your work go faster. It can make problems that are hard to solve or impossible to solve on a single machine possible, and it's everywhere. And the second part is, well, how do I make use of Chapel's features to productively program in parallel, or productively program parallel hardware? That's kind of a mouthful. So the fact is, parallel computation is baked into the Chapel programming language from the get-go, and Chapel's multi-resolution philosophy lets you pick levels of abstraction to make use of various high-level to low-level parallel features. And if you take these two guiding principles, lots of powerful features fall out of them, and those are the features that we'll be covering today. So first, I want to convince you that parallelism is important, which Zoom is taking away my cursor focus every time someone joins. So one of the important reasons that parallelism is important is that you can greatly improve the performance of your programs or make them run much, much faster. So my colleague Michael has previously introduced the analogy of growing wheat. So a single seed of wheat, I am told, takes 3 to 4 months to mature. And if you grow one by one, a 1 acre field of wheat, from my estimates, it would take about 200,000 years or somewhere in that ballpark. The good news is, however, that you can grow every single one of these wheat seeds in parallel, and your whole field is still ready in 3 to 4 months. And so in that sense, we've achieved a huge speed up over the 200,000 years that it would take normally to grow, or without parallelism, to grow this wheat. And not only does it make your programs faster, but it also makes it possible to do things that you couldn't do before. So one of the things that at some point we did was benchmark the Arcuda project, which is a Chapel-based data science at scale framework. And we benchmarked it on a sorting. And the biggest sort that we were able to achieve was 256 TB bytes. That's like terabytes, but powers of 2, I think, in about 30 seconds. Now, if you look at that number, 256 TB bytes, that is such a big number. So that is way, way beyond the amount of memory that a single desktop computer has. And in fact, based on what I've found, this actually exceeds the amount of memory that the Linux kernel can handle. So a single machine very, very likely cannot handle this much addressable memory. And yet, 30 seconds is all it took when we scaled this to 8,000 machines. So a problem that previously wasn't possible was made possible by dividing and conquering it in parallel. Not only can parallelism speed up your code and let you handle bigger problems, you also almost certainly have access to parallel hardware. So based on a cursory examination of the Steam hardware survey, I've discovered that 0.03% of surveyed computers have one CPU, and the rest have more, which makes it that 99.97% of computers in the Steam hardware survey have more than one core available to them, and therefore are usable for parallel computation. And this might be slightly biased because people who install Steam and play video games might have slightly beefier machines. But I think in practice, the fact is, if you have a modern computer, you almost certainly have parallelism available to you. And if you have a GPU, you can use that GPU for parallel computing because that GPU has a ton of tiny cores. And that's what the screenshot of this article that I'm including here discusses by Ahmed Rezai. So in fact, you have access to parallel hardware. And if you are in an HPC context, you also have access to parallel hardware and much more. So the fact of the matter is, HPC machines and systems also have multiple cores, and many of them have GPUs. So you still want to make use of that parallelism. But there's also even more concerns to writing performant parallel code on these machines. So these machines might have multiple network interfaces and CPUs, which can cause non-uniform memory access or NUMA effects. And in fact, when you're in an HPC context, you almost certainly want to parallelize your workload across multiple nodes. And within those nodes, you still want to make use of CPU level parallelism and maybe GPUs. And that brings us to Chapel, which helps you do all these things in a unified way. So this is a tutorial, but the fact is I don't know your background and I only have 30 minutes to talk about things. So what I will be doing more so today is providing a high-level overview, advertising many of the features that Chapel has. And then we'll have, as Brandon mentioned, more specific tutorials today and tomorrow. So on this slide here, I have a picture of the program I pulled from the ChapelCon website, which covers the first day and includes the I/O parallel loops, data structures, and distributions demos that will follow this presentation. So basically, if you see something here and you find it interesting, there will almost certainly be a tutorial today or tomorrow that will cover this. And now more about Chapel. So the problem that Chapel solves in a way is that there are so many technologies and ways and models for programming various parallel concepts. So you have multi-core programming. We've talked about with multiple cores. So pthreads and studthread and C++, Rayon and OpenMP all help you write code like that. You also want to program GPUs. Like I mentioned, if you have a GPU in your gaming computer, you have parallelism available to you. For that, you can either use the lower level CUDA and HIP libraries from NVIDIA and AMD respectively, or you might use something that wraps them, like PyTorch or NumPy or any of the technologies listed in this bullet. And maybe if you have multiple nodes or machines, you want to distribute your computation across them and use MPI. And a colleague of mine, Engin, specifically in the context of GPUs, presented this particular slide, which kind of shows you the landscape of these technologies. So to make use of multiple types of parallelism, like GPU and distributed memory, and just in general distributing your computation, it tends to require a whole variety of different frameworks that are positioned somewhere in this map. So you might want like CUDA or HIP, or maybe some kind of wrapper to write GPU programs, and then you want to use MPI and OpenMP or something like that to distribute your computation. And because of all this kind of heterogeneous nature of things, it becomes very hard to program productively. And so Chapel is designed from the ground up to kind of unify and make parallel programming productive in many contexts. And this is basically guided, in my view, by two major principles. So the first principle is parallelism by default. So whereas other languages provide parallelism kind of on top of the language, like in the library or something else, Chapel keeps that at the forefront of the language. And moreover, Chapel is a multi-resolution language. So it provides very high level and elegant and productive parallel programming constructs. But if you ever grow out of those and need something more, or something more advanced or more complicated or unusual, it also provides lower level control still built into the language to help you develop that. And many of the features we'll present today will be kind of consequences of these decisions or design goals, in my view. And by the way, I'm mentioning these here because I think that these two principles are important to understanding like the Zen of Chapel, and they should kind of guide how you feel about programming in the language. And today I'll cover the following features, which I find important and unique to Chapel. So here I've actually underlined words that indicate in which way these principles or these features descend or fall out from the principles on the previous slide. So we'll talk about locales, which describe where a computation could take place and where data could be stored. They are deeply ingrained in Chapel. We'll come to those shortly. Distributions provide recipes for both representing and distributing data. In particular, distributions apply to arrays and domains. So distributed, sparse, and GPU arrays in Chapel are all just arrays, and the language knows how to treat them specially when they need it. We'll then talk about we'll talk about parallel loops, parallel iterators at a bit more low level, which enable data structure specific parallelism. So you can write generic and high level code that picks the appropriate parallelization method depending on the data structure you're using. And then we'll talk more about the low-level features that are used to implement these high-level features that you can use to get explicit control of your computation. Throughout this, Chapel has a parallel standard library, which enables parallelism that is on by default. One example is the standard library sort, which is parallel and which my colleague Michael has written about. And Chapel also provides a global memory view, which makes it much easier to access data both locally and in a distributed manner in a uniform way. So you don't have to explicitly send messages or fetch data from other places. And I've talked a lot about Chapel as a programming language, but if you don't know what it is, then, well, here's the first little taste of it. Here we have two programs, one in Chapel, one in Python, that basically encode the same program. So Chapel has many of the features from traditional programming languages. It can create aggregate data structures. So here we have a pair of things, which one is an integer and the other is a string. And then we're using that. This data structure also has a method called foo, which prints out like a tuple formatted version of this pair. That's the same thing that the Python program is doing. Chapel also has variables, just like Python. In this case, var_p is a point with two values, 42 and hello, the same thing in Python. Though you might notice that in Chapel records are conventionally lowercase named. So the first M is lowercase. And the second variable is an array. In Chapel, I create an array of 10 my pairs and use their default constructor, which creates pairs with x being 0 and y being the empty string. And in Python, you can't declare arrays like that, but you can use a list comprehension, which is what I do to achieve a similar effect. So today, the talk will be mostly about parallelism-specific features, which leaves some of them important, but relatively more traditional features out. If you want to learn about I/O or aggregate data structures, such as records and classes in Chapel, you can scan these QR codes, which will point you to the times in today's schedule when these will occur. So I believe Lydia will be covering input and output, which includes reading, writing, and formatted I/O. And Jade will be covering aggregate data structures, which covers records, classes, and memory management. All right, and then now in the rest of the talk, I'll be talking about the unique parallel features of Chapel. And during these days, these features will be covered in depth. And I'll also be providing QR codes that link to the Chapel program that has precise times for these, though that will be happening in this meeting today or tomorrow. And now we can talk about locales. So a locale, I've mentioned earlier, is a representation of where computation is run and where memory could be stored. So you can kind of think of a locale for now as a compute node. So like in this picture, a locale might have processor cores, one or more, and memory to store variables in. And locales help encode important concepts in parallel computing. So specifically, where should tasks run and where should data be allocated? And this is in addition to which tasks should be run simultaneously, which is another aspect of parallel computing. So in this picture, I have a representation of 4 nodes connected to each other, and in the first core on the first node running some code. That's the spinning gear. So one way of parallelizing your program is to run computation on every single available node. So here, I've distributed the computation, but only one core on each machine is running it. If you really want to make the most use out of all your resources, you want to use every core on every locale that you have available to. And the next concern, besides running code, is where to store data. So in this picture at first, I have an array represented by 4 squares stored in locale 0, excuse me. But like we mentioned earlier, for instance, in the Arcuda example, this array could be huge, say 256 TB bytes, and you don't want to store all of that in a single memory, or maybe you just can't. So another way to store this array is to store pieces of it across various locales. So here I have the first piece on locale 0, the second piece on locale 1, and so forth. For performance reasons, if your array isn't too big to store in memory, you actually might want to replicate this array across every single node so that you don't have to communicate to retrieve values for your computation. And locales provide a language to describe these kinds of configurations or to talk about places where things can be stored or where computation can take place. And I mentioned GPUs earlier. GPUs are also fit into this locale model but the fact is GPUs are kind of like tiny computers because they have their own cores and they have their own memory. So when we represent GPUs using locales, we actually represent them as sublocales. So a single node like locale 0 might have 4 GPU sublocales if it has 4 GPU nodes. And those themselves will also have cores and memory and will be addressable from Chapel's locale features. So here I have an example of 2 connected nodes. Each of them has 4 GPUs. And I have some code that manipulates variables and uses on statements and locales to control things. So here is the current locale, which by default, since our gear is on locale 0, is locale 0. So the first statement declares the variable a on the first GPU available in locale 0. So that leads to a being declared here. And the second statement makes a copy of a on the second GPU. So that's this arrow moving b or copying b to GPU 1. Finally, I use an on block, which executes code on a particular locale to create a variable c, which is every number in b squared. So 1, 4, 9, 16, 25. And doing so because this can be promoted or because this is a potentially parallel computation will actually be executed by every single core on the GPU, and the memory will be stored on that GPU. And finally, I use another on statement to transfer execution to locale 1. So the gear is now in locale 1, and create a copy of the GPU array in the other node's memory. So in this way, we've allocated various arrays in various GPU memories and also transferred the memory to a different locale. And locality is a central notion to Chapel. So all code is executing on some locale, and you can always figure out which locale that is using the here variable. And all variables have a locale on which they're stored, which you can figure out by using .locale on the variable. Now I'll start talking about arrays, domains, and distributions. So arrays are a core data structure for many parallel tasks, and Chapel's arrays are fittingly very general and allow you to control how they are represented, iterated, and indexed. So a key property of arrays is their domain, which can describe their shape. So that includes the array's dimensions. It can be 1-dimensional, 2-dimensional, 3-dimensional. You can keep going, as well as the array's size. So you can have a 1x10 array, which I've written 1x10, but really it's just a 10-element 1-dimensional array. Or it can be a 200x200 2-dimensional array. And in this case, I have a variable declaration for array A1, which has 4 numbers, and this little picture here that encodes that. And then I store the array's domain, which effectively encodes the array's shape of 1x4 elements. And then, as I mentioned, arrays can be 2-dimensional. So the domain D2 creates a 8x4 shape. And then we can declare multiple arrays, all sharing that same domain. Here, these arrays are called A, B, and C, and they will all have that shape. This is helpful if you want to make sure that 2 arrays you have compatible size. So if you index into one, you can also index into the other. Domains do more than describe an array's shape, however. They can also describe how to index the array. So for some reason, it's convenient to 0-index your arrays, but for others, it isn't. And for an example, here we have a domain D, which is a domain for a 2-dimensional array. And then we have a subdomain of this with inner, which is kind of the inside portion of this. And here you have the code declaring both of those things. And the fact of the matter is, if you want to, since inner logically lies inside of D, when you access the top left corner of interior, the corresponding piece in the bigger array of D is actually not the top left corner, but the well, whatever this is, the top-ish, left-ish, one from the left, one from the top cell. And so when you declare arrays over these domains, everything, the array over the big domain, gets indexed at 0, and the interior array, which is an array with domain inner, gets indexed at 1. And this way, you can actually avoid various index manipulation to make sure that you're accessing proper parts of the arrays. In fact, domains can be mutable, and they can change. And all arrays associated with a particular domain can have elements come and go, or indices come and go if the domain changes. Arrays can also be distributed, which controls many other properties of the array. So the first property is where that array is stored. So far we've been talking about arrays that are stored on a single node, except brief mentions in the locale section where we split arrays. And however, we can also decide to split the array in equal chunks across all available compute nodes or locales, or we might want to split it round robin across all locales and so on and so forth. Previously, we've seen storing whole arrays on a particular node or in a GPU, but like we talked about before, big arrays may not fit it into any single node, so splitting them is crucial. In this diagram, I have an array A, which is split across 4 locales. Beyond that, distributions, or more specifically, a special case of them called layouts, can control how arrays are represented in memory. So by default, arrays are arranged consecutively in memory, so each element follows the other. But if you have a really big array, say, and this array is mostly zeros, but you want to have occasional non-zero elements, that's a sparse array. And instead of storing every single zero in memory, you can encode only places where elements are non-zero. These are called sparse arrays. And Chapel has 2 representations called compare sparse column, compress sparse column, and compress sparse row, which change the encoding of the array to be saved this way. And here I have pictures of other distributions and how they can help distribute arrays across different nodes. So in this case, an 8x4 array is distributed across 8 nodes, such that using a block fashion, which kind of takes chunks of it and spreads them to different locales. And then the cyclic distribution is the round robin that I mentioned earlier, where you basically walk through the array and assign the first element to the first locale, the second element to the second locale, and so on and so forth. There will be a demo of arrays, domains, and distributions later today. This QR code should link you to the section of the program that includes the time for this. And I believe Brandon will be covering it. Next, I want to talk about parallel loops. So these extend traditional sequential for loops with parallelism. And there's 2 main flavors at a high level. For each loops, basically only assert order independence. They basically say, hey, iterations ought not to affect each other, so you should be able to kind of do them at the same time. This kind of closely corresponds to vectorizable operations, or if you have GPUs, it corresponds to operations that can be translated to GPU kernels. So in this example, I'm creating a variable A on the GPU, so on the first GPU of the current node, and I'm creating it from a loop expression, which basically just squares the numbers 1 through 10. And this in Chapel will be automatically converted into a GPU kernel launch and executed on the GPU. For all loops are actually, I would say, more powerful. And the way they work is they invoke a parallel iterator of the thing being iterated. And this means that what a parallel for all loop does actually depends on the data structure that's being iterated. And many of Chapel's data structures have parallel iterators, and so have specified behavior for how they should be iterated over in parallel. But you don't typically have to worry about it because you can pretty much automatically parallelize the computation by iterating over any data structure with a parallel iterator. So in this case, I'm iterating over 2 arrays, A and B, and I'm setting each element of B to the corresponding element in A plus 1. So I'm just executing a +1 operation. And in fact, this is kind of redundant because you can use promotion, which allows you to apply scalar operations to things with iterators, and you could have written this as B equals A plus 1. But I was just being precise. And so we talked about distributions and parallel loops, and in fact, these two work together. So a block distributed array has a parallel iterator that instructs the for all loop to distribute the computation across multiple nodes and run the computation in parallel on all available cores. So we saw this picture earlier in the locale section where an array is split across all 4 nodes and pieces, and every single core of every single node is doing some processing. And that's exactly what happens when you have a block distributed array over all locales and you use it in a for all loop. And you don't have to do any more thinking about it. In fact, parallel loops are very high level and they make a lot of decisions pretty much for you. So how many tasks are created? And tasks are basically units of parallel work. Well, the data structure figures out how many tasks are needed. Often this is exactly how many tasks as your computer can run in parallel, but in theory it could be less or more. And then the data structure's parallel iterator also decides which tasks gets which pieces of the work. So which elements are processed by every core, for instance. And furthermore, the parallel iterator decides what nodes, devices, or domains that code has to run on. And this means that a regular array would run typically on a single node, but if you have a distributed array, that iterator will automatically distribute the computation over multiple nodes. And so a lot of the time, for all loops are basically fire and forget. And if you have generic code written using arbitrary types and for all iterators, you can basically have code that automatically works correctly in parallel. Shreyas will be demoing parallel loops later today, and he will cover for each loops and also co-for all loops, which are slightly lower level. This QR code should take you to the section of the program where the time of this presentation is given, but it's definitely today. And then I'll briefly mention lower level parallel constructs available in Chapel, which are co-for all loops, which spawn exactly one task for each iteration of the loop. So you can control exactly how many tasks you spawn. Typically, you would spawn exactly as many tasks as there are, as your computer can do in parallel, at least if you're trying to use all your cores efficiently. If you have parallelism or tasks that aren't similar to each other, you can just use a co-begin statement, which executes every statement in its block in a new task. So here, foo and bar will be executed in different tasks. And also, if you want to write more traditional or low-level HPC idioms or parallel idioms like locks, Chapel provides atomics, sinks, barriers, and other similar things to help you write lower-level computations. And in fact, the high-level features that we've talked about are implemented using these lower-level components. So we don't have tutorials on sinks and atomics, but the blog posts about Advent of Code from day 11 and 12 cover sync and co-for-all variables and barriers, as well as atomics. So you can scan one of these 2 QR codes to read more about those in a problem-solving context. And that brings me to the conclusion of the presentation. So I've told you basically the answers, in my view, to 2 questions. Why is parallelism important? And the fact is, it can speed up your work and make you able to do problems that you couldn't do at a smaller scale. And it also is required to make efficient use of your desktop and HPC machines. Furthermore, I told you how you can use Chapel at a high level to use these parallel concepts. This includes using locales and on statements to control about where execution takes place, using arrays, domains, and distributions to encode data, distribute it across nodes, and also store it in appropriate and efficient ways. You can use high-level parallel loops to quickly and easily get parallelism from your data structures. And if all of that fails, you can go to low-level features like co-for-alls, atomics, and so on and so forth to implement parallel idioms at a lower level. And all of that is possible because Chapel bundles parallelism from the get-go and has it integrated into its initial design, making it possible for you to express a variety of parallel tools or parallel computations. And that concludes my presentation. So, wow, that's just in time to move on, I suppose.
Awesome. Thanks, Daniel. We have 1 minute. So if anyone has a question for Daniel, please feel free to hop off mute and ask. You can also put questions in the chat. We can get answers to them as well. I'll hold for a second. Okay, great. Well, thanks, Daniel. I'm going to stop the recording and I will pass it to